What happens with the Q-treat? Well, it's pretty much the same. Now you will have each experimental context will be isomorphic to a Boolean algebra of 3 elements. But now this guy's here, I put the old Boolean algebra just to compare. It's isomorphic, but these ones are sets and these ones are projection operators. The difference between the quantum and the classical cases is that the quantum case cannot be reduced to one measurement context. You need infinitely many measurement contexts in order to define the quantum state. Well, in order to figure it out, you need not infinitely many, but I will not enter into that. But the thing is that you will have a pasting of Boolean algebras, which is not Boolean when you look at it from above. When you look at it locally from each experimental context, it will be a Boolean and you will recover classical probability. But the whole thing is not classical. Another way to put it is that quantum states can be considered as families of infinitely many classical Kolmogorovian measures. But they are pasted together in a very harmonic way. And there's a lot of research on that because you want to know how this pasting comes about from a mathematical point of view, because it's meaningful for experiments, because you can compare quantum theory with other alternative pastings and theories and try to see how the correlations are. So you can discard theories and ask which are the axioms that singularize quantum mechanics out of all possible conceivable mathematical models. So, well, I will jump this because I think it's too mathematical. Now, entering to the last part of the talk, I will speak about von Neumann. So, he says that, and one also has the parallelism that logics corresponds to set theory and probability theory corresponds to measure theory, and that a given system of logics, so given a system of sets, if all is right, you can introduce measures, you can introduce probability, and you can always do it in a very many different ways. Okay. And he says, in the quantum mechanical machinery, the situation is quite different. Namely, instead of the sets of use the linear subsets of a suitable space, say of a Hilbert space, the set theoretical situation of logics is replaced by the machinery of projective geometry, which is a very definite, again, geometrical object, which is in itself quite simple. So here again comes the connection between logic and geometry and probability theory. So in order to have probability, all you need is a concept of all angles. I mean angles other than 90 degrees. Now it is perfectly quite true that in geometry, as soon as you can define the right angle, you can define all angles. Another way to put it is that if you take the case of an orthogonal space, those mappings of this space on itself, which leave orthogonality intact, leave all the angles intact. In other ways, in those systems which can be used as models of the logical background for quantum theory, it is true that as soon as all the ordinary concepts of logics are fixed under some isomorphic transformation, all of probability theory is already fixed. So then he concludes, this means, however, that one has a formal mechanism in which logics and probability theory arise simultaneously and are derived simultaneously. This was a project of von Neumann, study the connection between logic and probability, and of course, all is made through the machinery of geometry. He chose a generalization of projective geometry in order to do that. We have made some research on this. You can check the papers afterwards if you want. But, well, it turns out that here comes the last part of the story, which is this the end of the story? No, because von Neumann didn't like it, Hilbert space formalism, for many reasons that I will not discuss. But he started to look for alternative quantum models, new mathematical formalism that did quantum-like theories but are not strictly equal to quantum mechanics. And they found them. In a series of papers, Murray and von Neumann searched for algebras more general than those which appear in quantum mechanics. These new algebras are nowadays called von Neumann algebras, and their elementary components can be classified as type 2, type 1, and type 3. And classical and quantum models are included in this machinery because all classical probabilistic models can be described as Boolean or abelian von Neumann algebras. So this machinery is a generalization of classical probability theory and includes quantum probability theory. So further work revealed that a rigorous treatment to the axiomatization of systems with infinitely many degrees of freedom in quantum mechanics needed the use of more general von Neumann algebras. So I will jump the mathematical details, but the important thing is this. Now you can give the axioms of a generalized probabilistic theory, which is like this. Start with an algebraic structure, L, that represents all the propositions that you can make about your system, about the outcomes from your system. So a state will be a measure from this to the interval 0, 1, satisfying the usual axioms of measure theory. When this lattice is Boolean, we get classical Kolmogorovian probabilistic theory. When it is not Boolean, we get a departure from the classical case. In the case of quantum theories, we get a very specific mathematical structure, which is, for example, those lattices that come from von Neumann algebras. But one can conceive more general models. And here I put some drawings. Remember that the coin was geometrically represented by a line segment. The qubit was all points here are quantum states, but the geometric shape is that of a sphere. But one could conceive more general models, at least in an ideal sense. Why not? And then you can speak about generalized probabilistic theory, in which you have convex sets associated to probabilistic models and so on. And the shape is very important here because it is connected with algebra. Remember the isomorphism between the faces of a convex set and the lattice of propositions. So, but then, if one can conceive more general probabilistic models, one may ask, which is the right axiomatization for probability theory in all applications? Quantum mechanics show us a domain of phenomena in which the more natural way to work is to assume that we have non-Kolmogorovian probability, because quantum states in this sense are non-Kolmogorovian measures. But then one may ask, is it possible to find violation of the Kolmogorovian model outside of quantum mechanics? Or in a more correct way, is it useful to use them outside of quantum mechanics? Well, in the last years, there are many research in that direction. Many researchers are trying to study quantum-like models in applications to problems in biology, cognition, economics, and so on. So one question is it possible to give a unified approach to all those applications? Are those applications really useful? Of course, they are possible. People do that and they can model what happens. In principle, they work. But the question is, should people change and move onto this framework or not? In the quantum case, I have no doubt about it. It will be a complete mistake to use classical probability and in the usual sense to describe quantum phenomena. It is more comfortable to use quantum states. But this opens the question about, is it possible to use it outside the quantum domain? So we have made some research about this. You can look at these references, and this has implications, because if you change the underlying probabilistic theory, you will get a different information theory. Quantum information theory is really different from classical information theory. This is why it is very promising as a technological development, and many governments and companies are investing a lot of money in order to build quantum computers, quantum communication systems, quantum internet, and so on. So we have worked out an interpretation for all this, for the generalized probabilistic models approach, which is, suppose that there is an empirical scenario in which a rational agent, which could be an automata, this has nothing to do with consciousness, must take a decision. And with that aim, he must define a degree of belief function. How likely is that this event will happen or not? So different possible experiments or results are available, and they are organized in an event structure, like in classical probability and in quantum mechanics, assumed to be an orthomodular lattice. If the lattice is Boolean, then we prove that you recover, using Cox's approach, it is possible to prove that you recover Kolmogorov actions. But on the contrary, if the states of affairs that the agent must face presents non-classical features like contextuality, it is more natural to use a non-Kolmogorovian probabilistic calculus. And the natural information measures will be Shannon's in the Boolean case, and in the quantum case, it will be von Neumann's entropy. And you can define generalized entropic measures for more general theories. Well, this is a summary. Here you can check the references of Cox's work, and this is our work for the quantum case. So I will jump this because I think that I have no time. So this as a model for epistemology, what will be? It is that if you get a theory, like quantum mechanics, then the theory defines what is experimentally testable. It will tell you which are the experimentally testable propositions. In quantum mechanics, are projections are represented mathematically, but projections acting on a Hilbert space. And then, out of this, you define all possible compatible measures, compatible with the algebra of propositions. And then you will get the geometry of the set of states. And the same for a classical theory. But now come with a different theory, and you can play the same game. So it will be like a general structure and underlying probabilistic theories. I will jump this. Just to end up, you might question what are classical probabilities in a quantum domain. I already said this, but I think it is important to say it again. Classical probabilities are not gone, because this lattice here, the whole propositional structure may be non-classical, non-Boolean, but a concrete observable has to be Boolean. Each time you make a concrete experimental setup, you put everything in the table of your lab, arrange the laser. Once you specify that, you will get a classical probabilistic distribution. So this guy here is not Kolmogorovian. You have non-Boolean, non-Kolmogorovian measure. But when you make the composition of this guy with a concrete observable, you get a classical measure. So each generalized probabilistic model will be a family in the sense of being an harmonic pasting of classical Kolmogorovian probabilistic measures. But the whole thing is not classical. So just to conclude, we have discussed the formal structure of probabilities in quantum mechanics. We have seen that these probabilities can be considered as non-Kolmogorovian in the sense that the sigma algebra is no longer a Boolean one. Thus, one can speak of a non-commutative probabilistic calculus that can be suitably generalized. This has implications for many disciplines, especially for information theory. A concrete example is quantum information theory. Here you can find, of course, if you send me an email, I can send you the papers, no problem. A list of references of our work in which we have discussed this largely, and all the technical details that have no mentioned in this talk. And well, that's all. Thanks for your attention. And before finishing, I would like to make a comment, which is that every year in Argentina, we change city, but it is always in Argentina, we organize a conference on quantum foundations that gathers physicists, philosophers, and mathematicians. So if you are interested to come, you are welcome. Next meeting will be in Cordoba from 27 to 29 of November of this year. And next year, for students and people interested in researchers interested in learn about quantum mechanics, in April we organize the school called Quantos, which is a school on quantum mechanics and quantum information theory. And of course you are invited to come. So if you are interested, just send me an email and I will send you the details. Well, thanks for your attention. Any questions or observations? Otherwise, we can move on to the coffee break.
So this is something I've always wondered.